Welcome, learners. It gladdens my heart to welcome both old and new students to this channel. Remember, this is the platform where you learn the sciences. If you are studying for your MSCE examinations, this is the platform where you come and learn the sciences to prepare you fully for your MSCE examinations. Remember, the aim of Global Black Slides Online is to make sure that everyone has access to science education, all right, so that you succeed in your MSCE exams. So we are in solidarity with the government of Malawi that every child, regardless of background, must have access to quality education. All right, so here on Black Slides, we are offering quality science education. You learn the sciences here on YouTube for free, but in case you want extra support, then you have to enroll into the main class, the main online class, which is called Black Slides Online Secondary School. Simply get in touch with us using the numbers that were shared before. Without wasting much of your precious time, would like to dive into the lesson of the day. All right, this is just introductory lesson to the topic called magnetism. Magnetism. All right. The general objective of this topic is for you to be able to explain the relationship between electricity and magnetism. Remember, the relationship between electricity and magnetism is called electromagnetism. All right, we shall dwell on a number of issues. We'll look at the principle of the electric motor, the working of the electric motor, the DC motor. We'll discuss the motor effect. We are going to discuss quite a number of aspects of magnetism, electricity and magnetism. All right, so welcome to the subtopic, the principle of the electric motor. How does the electric motor work? You will be asked in your exams, especially in paper 2, either question 1 or question 2. The examiners will ask you to describe how the DC motor works. So in this topic, in this lesson, we shall explore the working of the electric motor, the principle on which the electric motor works. All right. So by the end of the topic, it's quite a big topic. You should be able to demonstrate the existence of a force, on a current carrying conductor in a magnetic field. So we are saying you should be able to recognize the fact that a current carrying conductor in a magnetic field experiences a force. All right? That's a very important point to note. So we expect you to be able to demonstrate that a wire which is in a magnetic field will experience a force. Okay, let's suppose that we have two magnets such that one end is north pole, the other end is south pole. So suppose we have a wire which is passed across the magnetic field. So between these two magnets, there's a field. There's a field. All right. There's a field, magnetic field. All right. Now, let's suppose that this wire is connected to a source of power, let's say a battery, for example, a battery. All right. So, assuming that we have a circuit like this, such that we have a wire, this is a wire, which is passed in a magnetic field. So we have a field, this is a field, a magnetic field, shown by the magnetic field lines. So once the circuit is completed, then the wire will be seen to move up and down. This movement of the wire, which is passing through a magnetic field, is due to the interaction between the electric current and the magnetic field. So a wire which is passing through a magnetic field is going to experience a force. All right, so by the end of the lesson, you should be able to explain that fact. You should be able to explain that fact. All right. We are also going to look at the use of Fleming's left-hand rule to predict the direction of such a force. Don't worry about this. The Fleming's left-hand rule is going to come out clear as we go along. As we continue with the lesson, Fleming's left-hand rule. All right, you are going to investigate the factors affecting the size of the force. So, what could be the factors that would either increase or decrease the magnitude of the force on the current carrying conductor? And then you should be able to explain the operation of moving coil instruments, such as the speaker, for example, the loudspeaker. How does it work? So all that is going to be covered in this topic. All right, so welcome to the motor effect. The motor effect. All right, in order to understand the motor effect, we are going to look at a force on a current carrying conductor in a magnetic field. A force on a current carrying conductor in a magnetic field. Earlier on, I showed you a diagram, this one. Suppose that we have two magnets such that one end is North Pole, and we have another magnet with a South Pole. So when two magnets are brought into the vicinity of each other, like close to each other, there is a field. There is a field which is called the magnetic field. So there's a field between these two poles of magnets. Remember that we use field lines to represent magnetic field. All right, so if we pass a wire, suppose we pass a wire. Sorry about this. Yeah, let's suppose that we pass a wire. This is a wire, such that this wire carries electricity. Suppose we have something like this. All right. This is a wire. Let me color it nicely so that we don't get lost on the way. Maybe green is going to help. Yeah. Suppose this is our wire which is carrying current. Okay. Suppose we have a setup like this. Let's say we have a switch over here, and this is the power, or like a cell maybe. Yeah. And over here we have a wire. So when the switch is closed, close the switch, current is going to flow through the wire, like that. Current is going to flow through the wire. Okay? And so we are going to discuss a force. When the switch is closed, the wire would be observed to move up and down. It's going to be seen to move up and down, up and down, up and down, up and down. All right? And that's what we are talking about here. Force on a current carrying conductor, such as this wire here, in a magnetic field. All right, I just wanted to give you a picture, general picture, to get you into the general perspective of the lesson. All right, welcome once again. So when a conductor carrying current is placed in a magnetic field, it experiences a mechanical force. All right, what we're saying is we have two magnets. One end is North Pole, the other end is South Pole. Remember, between two magnets, there's a field. Two magnetic poles, there's a field, magnetic field. And we also recall from your Form 2 physics that magnetic field lines point away from the North Pole towards the South Pole. All right, from the North Pole to South Pole, like that. So there's a field here, which we can represent using lines, field lines. All right. Now, suppose that we have a circuit, part of which is a straight conductor, like wire. Suppose we get this connected to, let's say this is a switch, and this one here is a cell. Yes. So when the switch is closed, for sure current is going to flow through the conductor. So it is this conductor which is placed in the magnetic field. So we are saying, we have a point here which is saying, we are saying that when a conductor which is carrying a current is placed in a magnetic field, it experiences a mechanic force. It is going to experience a force. You would be visually able to see. Visibly, you will see the wire. This wire will be seen to move, to jump up and down. You would see this, you would appreciate this one. So there is a force, F, acting on the conductor. You would visibly see the wire moving up. You will see the wire moving up in the direction that I've shown there. So the direction of this force on the conductor, the direction of the force can be understood using what is called Fleming's left-hand rule. All right? So we're saying the direction of the force, which is also called the thrust, on the conductor is predicted using left-hand rule. What does Fleming's left-hand rule state? Your examiners will not spare you from stating Fleming's left-hand rule. They will ask you state Fleming's left-hand rule. So you have to know the statement of Fleming's left-hand rule by heart, like you have to know all other rules, laws in physics, principles, and so on. So the statement of Fleming's left-hand rule says that if the first finger, can you try to hold your fingers like shown here in the diagram? If the first finger, the second finger, and the thumb of the left hand are placed at right angles to each other. Notice, at right angles to each other, with the first finger pointing in the direction of the field. So the first finger is going to point in the direction of the field. This is your first finger, by the way. It's the one that is close to the thumb. That's the first finger. All right? So the finger is going to point in the direction of the field, like that. The second finger is going to point in the direction of current. The second finger is this one. Then the thumb is going to point in the direction of motion of the wire. So your thumb is this one here. So if you look at the word first, F stands for field, depicting the direction of the field, the magnetic field. Yes. If you look at this word second, making the letter C capital, then the second finger C is going to represent the direction of the electric current. And lastly, the thumb capitalizing M, will represent motion of the conductor in that particular field. So here we are saying that the finger, the thumb, the first finger, the second finger, and the thumb are perpendicular to one another, like shown here. All right? So we are saying the first finger points in the direction of the field. The second finger points in the direction of the electric current, while the thumb points in the direction of movement of the wire in response to the force that the conductor experiences. Once again, my name is Mr. Paul Chilola. All right, so we have a scenario here which I just explained. So we have a wire, which is our conductor, and then we have magnets, two magnets, one north pole, the other one south. So remember, between the two magnets there is a field, which we can use lines to represent. Yeah. So there's a field. And the wire, the conductor, is passed between these two poles of a magnet. So when we close the switch, when the switch is closed, when the switch is on, current flows through the wire AB. So we have a wire. The wire here is this one here. And by the way, this must be connected to a source of power, cell. Yeah, so we have A and B. So the switch, we can place the switch somewhere here. Yeah, that's our switch. All right, so we are saying that when the switch is on, current flows through the wire AB. All right, and the wire jumps up in response to the interaction between the field. Remember, we have a field here. We have a field. So the wire jumps upwards. The direction of the movement of the wire can change depending on the direction of the magnets or magnetic field, or the direction of the polarity of the cells or battery. All right, so we are saying that the wire jumps up in the first place, and if the direction of the current or the magnetic field is reversed, the wire reverses downwards. The wire moves downwards. All right, so let's suppose that we swap the poles. Here we have north pole. Let's suppose we have north pole here, and then we have south to this end. Then the wire is going to go down. It will also go down if we change the polarity of the cells. Let's suppose that one end, instead of having negative here, we have negative here. We have a positive terminal at the end. The wire is also going to change direction. Take note of these points, because your examiners will ask you, give you situations, scenarios for you to explain. All right. Now, the magnetic field due to the magnets, and the current carrying wire can be shown in the diagram here. All right. So we have the north pole on one end and the south pole this end. And then we have magnetic field lines, these lines here. Remember, magnetic field lines point away from north towards the south pole. And then we have a wire. And then we have direction of current. So the wire will be seen to move up, upwards. The field due to current carrying wire is indicated by the circles carrying the dotted, while the dotted lines are the fields of a magnet in this diagram. The resultant field obtained by combining both fields is now shown here, down here. So the wire is going to be seen to move upwards, and the magnetic field lines will be seen shown by the arrows. Here we have the arrows pointing in the direction of the field. So there are more field lines below the wire since both fields act at the same direction, but fewer above it because they are in opposite direction. Okay, let me take you back a little bit. That just to remind you that a current carrying wire also has a magnetic force. So the magnetic force due to the current carrying wire plus the magnetic force due to the two magnets, these interact one another. The effect is to produce a resultant force which will cause the wire to move upwards. So if we suppose that field lines to be stretched elastic material, those below will try to straighten out, and in so doing, they'll exert an upward force on the wire. Take note, we are saying that there are more field lines below the wire since both fields act in the same direction, but fewer above it because they are in opposite direction. All right? So if we suppose the field lines to be stretched elastic material, those below will try to straighten out, and in so doing, they exert an upward force on the wire. So the wire moves up because of the interaction of the two field magnetic fields. One magnetic field created by the current carrying wire due to the current through it, and the other magnetic field is the one between the two magnets. So take home the fact that a current carrying wire passed in a magnetic field would experience a force, and that force can be observed upon seeing the wire moving mechanically. Factors affecting the magnitude of the force on the current carrying conductor. What are the factors that influence the magnitude of the force? All right, whether the force is big or small depends on a number of factors. The magnitude of current flowing through the conductor. The bigger the current, the greater would be the force on the wire. And also the field strength of the magnet. The bigger the magnetic field, the greater would be the force on the wire. And also the length of the conductor exposed to the magnetic field. A longer wire would experience a greater force. Why? Because it means more current is passing through it. The angle of inclination, the angle at which the current carrying conductor is to the magnetic flask. The force is maximum when the direction of the current is perpendicular to the magnetic field lines. All right, so if the wire is bent at an angle, then the force will be less. Take note, they will ask you in an exam to state any two factors that would affect the magnitude of the force on a current carrying conductor. So know all these so that you can mention any two. So the effect of the magnetic field on a current carrying conductor is referred to the motor effect. So the effect we just saw, we just discussed, whereby we're saying a conductor is going to experience a force causing it to move when passed in a magnetic field, is called motor effect, the motor effect. So the motor effect states, therefore, in case they ask you to state, the motor effect is a simple statement. It says, a current carrying conductor placed in a magnetic field experiences a force. Oh, suppose you are asked to state the motor effect. A current carrying conductor placed in a magnetic field is going to experience a force. This effect can be applied in a number of places. Namely, it is the basis for the working of a loudspeaker, which we are going to discuss later. It is a basis for the working of the DC motor. It is also a basis for the working of a moving coil galvanometer. These devices work on the basis of the motor effect. What does the motor effect say? The motor effect states that a current carrying conductor placed in a magnetic field experiences a force. We shall look at each one of these one at a time in our next lessons. For now, let me leave you. It has been wonderful to present this lesson to you. If this is the first time you have watched these video lessons on YouTube, consider subscribing to the channel. Remember, our goal at Black Slides is to have as many students as possible pass with distinctions in the sciences, namely physics and biology, physics, chemistry, and biology, as well as mathematics. So once again, my name is Mr. Paul Chilola, your teacher. Consider also enrolling for online lessons. We are going to be glad to have you there. There is so much learning taking place there, and we have notes that we give out to our students. We have lots of exercises and the different learning materials. So welcome once again. Bye-bye for now. See you in the next lesson. Bye.